Free convection and forced convection are two of the common mechanisms of heat transfer that is used for removing heat from heat sinks and components, hot bodies. Let us now consider an example to crystallize our understanding of this free and forced convection. Let us take an example of refrigerating a box, a volume of box. So consider this cylindrical box. I will take a cylindrical box like this, and we would like to cool the chamber inside. So now this cylindrical box is covered all round by thermocol, let us say. So the cylindrical box is tightly packed with thermocol. There is no way of heat coming out into the atmosphere or from the external ambient within the box. Now let us make a small opening there at the top of the box. So at the top of the box, what I will do is cut open an opening such that a Peltier element can directly fit in there, just fit in there. So let us place a Peltier element there, and the terminals of the Peltier element will bring it out through the thermocol, and then there I will terminate it with the appropriate electronics DC-DC converter, and I'll power it up with a photovoltaic panel or a module externally in this fashion. So the Peltier junction is getting its electric power. Job of the Peltier junction is to remove the heat which is there, whatever heat is there, out into the external ambient, such that once the heat is removed from this chamber starts becoming cold. So that becomes something like a refrigerator, a container which is a refrigerator. Now this portion will be the cold portion, and that will be the hot portion of the Peltier element. Now on top of the hot portion, I will place a heat sink. I will just place a block of aluminum, and this block of aluminum, because this is a cylindrical box, I will take a cylindrical shaped block and then place it on top of this aluminum like this, on top of the hot plate of the Peltier element in this fashion. So this is the aluminum block which will act like a heat sink. It will remove the heat from the hot side of the Peltier junction and put it out into the external ambient. Now all this portion which is in contact, all this metal body of the box which is in contact with the cold junction of the Peltier element will conduct the heat into this cold portion, and the heat from the cold portion into the hot junction will be pumped by means of this external electric power that we are giving to the Peltier element. So the heat flow will be like this. QC amount of heat from this chamber will be pushed into the aluminum block which is acting as the heat sink by the Peltier heat pump. Now let us say this aluminum block is having 11 centimeter height, and it is having a dia. It's a cylindrical block, aluminum cylindrical block. It is having a dia of 22 centimeters. Now let us say that we would like to maintain this aluminum block at 70 degrees. Now let us say that after 1 or 2 hours of working, it has reached a steady state of 70 degrees, and during that time the ambient temperature outside was 30 degrees. So now this is the situation. So this is the refrigerator that is working. Now let us try to analyze it and understand it from the point of view of forced convection, because when you are putting QC amount of heat into the heat sink, that much amount of heat plus the heat that is put from the electrical side through the Peltier junction E, the electrical power, both those should be put out into the ambient. So let us calculate that values and let us see how we go about doing that. For this example, let me say that I am measuring the input power from the electrical side. So I am measuring Vp, the terminal voltage across the Peltier element, and Ip, the current flowing through the Peltier element. So after measuring, I will calculate Vp into Ip, and I am finding it at around to be 10 watts, just for an example here. So there is no forced cooling. I have not placed any fan anywhere, so it is a case of free convection. So considering this as a free convection problem, and this cylindrical block being aluminum block, let us find out how much amount of heat is going out of this aluminum block. So in this aluminum block, there are only two possible surfaces. One is the top surface. From the top surface you can have heat going out, and on the side surfaces. So it's a cylinder, so the entire side surface, there also the heat can go out into the ambient. So those are the only two surfaces where the heat can go. Remember that we have placed thermocol everywhere, so there is no chance of heat going from any other direction. The heat can transact with the atmosphere, with the external ambient, only through this Peltier element, because everything else is covered up with thermocol. And once it has gone into the hot body, which is the heat sink, it can go out into the ambient only through the top and through the sides. So let us find out how much amount of heat is going out from the top and the sides. Then we will have an idea of how much of QC is going out through the Peltier element. So the top is a circular flat plate. So it is like a circular flat plate, and we had studied about the circular flat plate while discussing free convection. Recall that we had discussed about this while studying free convection for standard solids, the circular horizontal flat plate, where the diameter will become the characteristic dimension, and then we have the calculation for the Nusselt's number depending upon whether it is laminar flow or turbulent flow. And to calculate Nusselt's number, we need the Rayleigh number. So the Rayleigh number we had calculated, we had given a formula like this for free convection, and we had listed down all these parameters, what it is like. So let us use these formulas to find out the Nusselt's number, and thereby then later on the thermal resistance. So the Rayleigh number is given by this equation, G beta x to the power of 3 x cube delta T by the delta and nu here. So this is the diffusivity and nu is the viscosity, kinematic viscosity. So the values, G is 9.81 meters square per second, beta for air, this is the coefficient of thermal expansion for air, 1 by 330 for every degree Kelvin. X is the characteristic dimension. The characteristic dimension for a flat horizontal plate circular is the diameter d, which is in this case 22 centimeters or 0.22 meters. Delta T will be 70 degrees of the hot aluminum block, external ambient 30, so it will be 70 minus 30, that would be 40 degrees delta T, 40 degree Kelvin. Then you have the thermal diffusivity for air, I mentioned 2.6 into 10 to the power of minus 5 meters square per second, and kinematic viscosity 1.8 10 to the power of minus 5 meters square per second. All these data are available in scientific tables. beta, delta, nu are all available in scientific tables. So now if you substitute all these into this and calculate, you will get 2.7 into 10 to the power of 7. Now this is a value that is greater than 10 to the power of 5, and therefore I will use the Nusselt's number corresponding to the turbulent flow, equation corresponding to the turbulent flow, 0.14, Rayleigh number to the power of 0.33. Recall that for turbulent flow, horizontal flat plate, for Rayleigh number greater than 10 to the power of 5, we use Nusselt's number given by this relationship. So if you substitute for Rayleigh number, you can find out the Nusselt's number and it will work out to be 39.69. So next, let us try to find what is the power heat that is flowing out, heat flow in watts that is flowing out of the top plate. So we have the heat flow equation, which is conductivity A, area of cross section orthogonal to the heat flow, Nusselt's number by X. So let me move this up, by X into delta T. So this is the heat flow equation. Now we know everything. We know the thermal conductivity of air. We know the area of cross section of the circular plate on top. Nusselt's number is known, X is known, which is the dia 0.22, delta T is 40 degrees Kelvin. So if we substitute, let me do that. If we substitute these values, thermal conductivity for air I mentioned is 0.026 watts per degree Kelvin per meter. Area of the circular plate pi by 4 into d square, which is 0.22 square. Nusselt's number 39.69 into 40 degree Kelvin as the delta T divided by X, which is 0.22. So this works out to be around 7.13 watts. So this 7.13 amount of watts is the heat flow out of the top of the aluminum block, cylindrical aluminum block. We will call that one as Q top for now. So now let us calculate what is the heat flow out of the sides of the aluminum block. So let us now find out the heat flow from the sides of the aluminum block. So from the sides, if you see, it is like a vertical cylinder. So a vertical cylinder is something like this. We had discussed about the vertical cylindrical solid and the heat flow when it is placed in this fashion, and we know that the characteristic dimension is L, which is the height of the cylinder, and for laminar flow and the turbulent flow, the relationship for the Nusselt's number with respect to the Rayleigh number is given in this fashion. So X is 0.11 meter, which is the height of the cylindrical block. The Rayleigh number is given by 3.38 into 10 to the power of 6. Here it is the same. It is the same relationship that we use for the top. The only difference is in X. It was the diameter before. It was 0.22. And here it is the height, which is 0.11. Substituting, you have this relationship, this value. So this value is between 10 to the power of 4 and 10 to the power of 9. So we will use the Nusselt's number equation, which is appropriate for the laminar flow. Recall that for the vertical cylinder laminar flow, when the Rayleigh number is between 10 to the power of 4 and 10 to the power of 9, we use the Nusselt's number relationship here which is given by 0.56, Rayleigh number to the power of 0.25. So that is what we will be using. Substituting Rayleigh number value, you get the value of the Nusselt's number as 24.015. The area of the side cylindrical surface area of the cylinder on the sides is pi d h, or 2 pi r into h, is pi d h. So now we are ready to find the Q, the heat flow from the sides, given by K, A, Nusselt's number by X into delta T. All these values are known. We can substitute 0.026 for air, thermal conductivity. A is area of the sides of the cylinder, pi dh, pi into 0.22 into 0.11 into Nusselt's number 24.015 into delta T, which is 40 degree Kelvin, by X, again 0.11. So this works out to 17.26. So let me move this up a bit. 17.26 watts. So this is Q side. So from the sides of the cylinder, cylindrical aluminum block, which is acting as a heat, 17.26 watts is flowing out. From the top, we saw 7.13 watts is flowing out. So together, you see that the total heat flow to the ambient is QH, totally going out of the cylindrical aluminum heatsink block, which is Q top plus Q side. So this works out to 7.13 plus 17.26, which is equal to 24.39 watts. So much amount of watts is going out of the heatsink, and that is QH. Now how much is QC, which is the amount of heat going from the chamber? So recall this figure. QC is going to the cylindrical aluminum block, is being transferred by the Peltier junction. There is amount of E, electrical power, which also goes in. QH here will be QC plus E. So QC plus E amount is put into the external ambient, and that is 24.39 watts. So COP, coefficient of performance, we have seen earlier that it is QC by E. QC is the heat being extracted from the cold junction, in this the chamber, divided by the electrical energy fed into the Peltier element. Or I can write it as QH minus E by E, which is QH by E minus 1. So QH is known, we know 24.39. So that is 24.39 by, we said 10 watts you take for Vp into Ip, and if we put that value minus 1, you will get 1.44. This is the COP value. So QC value can be found out. Now QC is COP into E, which is 1.44 into 10, which is 14.4 watts. So around 14.4 watts of heat power is removed from the chamber, the refrigerating chamber, continuously. So the heat flow power QC is 14.4 watts. For the same problem, for the same refrigeration problem where we want to cool the inside of this chamber, let us now keep all things same. Let us say we still want to maintain this aluminum heatsink block as 70 degrees centigrade and the external ambient is 30 degrees centigrade, and we still supply 10 watts of electrical power into the Peltier element. Now let us see what happens if we include the fan and make it as a forced cooled system. So let us now include a fan which is going to blow air like this, and we now have a forced air flow. So now it's a problem of forced convection. Now let us say that this fan, you can get it from the fan data sheet, at a particular speed it is giving 3 meter per second velocity of the airflow over the aluminum block. Now how much amount of heat can you now draw out of this chamber for all things remaining same? So let us say this is the forced convection problem, and let us again consider heat flow from the top and heat flow from the side, because the heat can flow only from the top and the sides of the cylindrical block. All other regions and spaces are enclosed within thermocouple. So the top is like a flat plate, flat circular plate. So we have studied and discussed the flat circular plate. Recall that in the forced convection or a flat circular plate, the characteristic dimension is the length of that plate, which is in this case a circular plate diameter d. And for the laminar flow and the turbulent flow, we have the Nusselt's relationship with the Reynolds number. So let us calculate the Reynolds number. So for this circular plate, the Reynolds number is given by Ux by nu. Nu is the kinematic viscosity, U is the velocity of the airflow, X is the characteristic dimension. U is given from the fan data sheet 3 meter per second. Nu, the kinematic viscosity, is 1.8 10 to the power of minus 5 meter square per second. This we know for air. This is for air. And the characteristic dimension is the diameter, which is 0.22 meter. Now, knowing all this, substituting, we can find that Reynolds number is given by 0.3667 into 10 to the power of 5. Now this value is less than 5 into 10 to the power of 5. Again, going back, recall that for laminar flow, Reynolds number is less than 5 into 10 to the power of 5. We will use this relationship. Nusselt's number is 0.664, Reynolds number to the power of 0.5, kinematic viscosity by thermal diffusivity to the raised to the power of 0.33. So Nusselt's number is given by this. So this is the kinematic viscosity and this is the diffusivity, and we will raise it to the power of 0.33, and calculating you will get Nusselt's number as 112.62. Now we can calculate Q, and we'll call that one as Q top. Let me move this up a bit so that you can see. Q top is given by the heat flow equation now, which is thermal conductivity A, Nusselt's number, by characteristic dimension into delta T. We know all these values, we can substitute. Let me move up the page and then let me write. Thermal conductivity for air 0.026. We have seen that area of the top plate pi by 4 d square into Nusselt's number 112.62 into delta T 40 degree Kelvin divided by X 0.22. So this turns out to be 20.24 watts. So 20.24 watts amount of heat flow is going from the top surface. Now let us calculate for the sides. What is the heat flow from the sides of the cylindrical aluminum block? Calculating the heat flow from the sides. Now the sides is like a vertical cylinder with forced airflow, and we have seen the relationship for a vertical cylinder with forced airflow. Recall this is a vertical cylinder which is having a diameter d. The characteristic dimension is d diameter, and you have placed a fan here, and for laminar flow it is this relationship. For turbulent flow, where Reynolds number is between 1000 and 5 into 10 to the power of 5, we have this relationship. So we will find out Reynolds number, and depending upon where it falls, we will use that particular Nusselt's number relationship. So x is the diameter, 0.22 meter. Reynolds number is ux by nu, which is 0.3667 into 10 to the power of 5 and this value is between 1000 and 5 into 10 to the power of 5. So this can be considered as turbulent flow, and we will use the Nusselt's number corresponding to that, 0.26, Reynolds number to the power of 0.6, nu by delta, kinematic viscosity by diffusivity raised to the power of 0.3. Now if you substitute, you will get 127.54. Now Q side, the heat flow from the sides can be found out from Ka Nusselt's number by x to delta T. Substituting, you have the thermal conductivity, the area of the sides, pi into d into h, into Nusselt's number 127.54 into delta T 40 degree Kelvin by x, which is 0.12, and this comes out to be 45.83 watts. So what is the total heat flow from the aluminum block to the ambient? We'll call that as QH, which is Q top plus Q sides. Which is 20.24 plus 45.83, 66.07 watts. Approximately 66 watts are actually going out from the aluminum block into the ambient, and this is the amount of heat that is coming from a combination of heat QC from the chamber and E from the Peltier electrical side. So let us look at the coefficient of performance now, which is QC by E, which is also equal to QH by E minus 1, which we worked out just earlier. QH is 66 by E 10 watts, let us say, is being pumped into the electrical port of the Peltier element. You have 5.6. Now you see that it is vastly improved from the 1.44 of the earlier case, free convection case. So forced convection improves the coefficient of performance. Now you see the amount of QC, that is the amount of heat that is removed from the chamber, is COP into E, which is 56 watts. Remember that we had just removed around 14.4 watts in the case of the free convection, and by putting forced convection, all else being same, you are able to remove 56 watts out of the amount of heat flow from the chamber, and the refrigeration will definitely be much improved, much better. So it becomes important that removal of heat from the hot side of the Peltier junction is very, very important, and you have to give sufficient attention to that if you want to make an effective Peltier cooling system.